Today we are going to learn a new chapter. The name of the chapter is Wave Optics. Now in our class 12 standard there are basically two part of syllabus in context of light. Basically the first one is ray optics and the second one is wave optics. Now why we are going to learn optics, the physics of related to light in two different ways. The first way is considering the light to be a ray, and the second one is considering the light to be a wave. Now, what is light basically? The light is basically, obviously, it's a electromagnetic wave, but it shows some ray nature. Now, whenever we are concentrating on the ray nature, and this topic is actually covered in the part 1. That means the physics of lens, the prism, and as well as the plane and the curved mirror. Now in this section, the part 2, we are going to learn the wave nature of light. Now basically light is a kind of electromagnetic wave. Now whenever we are using the word light, we mean that the visible region of the electromagnetic spectrum. Basically there are many other examples of electromagnetic waves like X-ray, gamma ray, and as well as the radio waves, microwaves, and these have different application in our day-to-day life. But obviously the most important part is the visible light, because without that visible light we cannot see actually. So that is the reason we are really interested to learn about that visual spectrum of light. Now the ray nature of the light was known to us even after. Now the wave nature of light was known to us even before the invention of the wave optics. That means the electromagnetic wave basically. So the wave nature is represented by the interference and the diffraction phenomena. Now the thing is that how we do know that light is a kind of wave? Obviously the answer is the refraction, the answer is interference and diffraction basically. So basically the ray nature is represented by reflection and refraction, and the wave nature is represented by the the wave nature is represented by the diffraction and interference. Now why interference and diffraction are really important to represent the wave nature? We'll learn about this portion whenever we will be learning the interference and the diffraction. But the thing is that first let us discuss about some basic theorem. Now before we develop the physics of electromagnetic wave, we already know that light shows the interference and diffraction phenomena, and we faced a problem regarding to explain this portion, because at that time we do not have the basic framework of the electromagnetic wave. We do not know what is electromagnetic wave actually, but we do know that light shows interference and diffraction phenomena. Now if light is showing interference and diffraction phenomena and we do not have the basic framework of the electromagnetic wave, there we required a new theory, and that theory was given by Huygens. Huygens helped us by providing a basic formula, you can say, or basic theorem or basic assumption by which we can actually explain both the ray nature of light and wave nature of light. Now the thing is that whenever physics is unable to explain some theoretical observation, physics started searching about new theory actually. Now the ray nature, the laws of reflection and the laws of refraction was enough to explain the reflection and refraction phenomena. But there was some problem. problem number 1, that to explain the reflection we require different law. To explain the refraction we require different law. Both of these law seems to be the similar, but these are not same. So we need to draw a connection between them, a bridge between them. Another problem was we was unable to give some proper explanation of interference and diffraction phenomena. So at that time, Huygens helped us by providing his famous principle. Now we are going to learn about Huygens principle. So before we start with Huygens principle, we should know something about the waves and wavefront. Now what is wavefront and what is wave? Now basically, I hope you all have ever seen a sea beach. I mean, whenever we are in the sea beach, some wave, some water waves comes to us, and obviously we can draw a line in the water if the water is coming towards us. So in the same way, if we put a stone or put something into the pond, some ring shaped structure or geometrical pattern is there. So this is actually called wavefront. That ring shaped pattern is actually called wavefront. Now wavefront, suppose is a point object, it generates a spherical wavefront. It generates a spherical wavefront. If there is a linear light source, it generates a cylindrical wavefront. And if there is a planar light source, it generates a planar wavefront. And that is all. So if this is a light source, then it generates a cylindrical wavefront. If this is a point source, it generates a spherical wavefront. And if this is a planar light source, then it generates a planar wavefront. Now there are different wavefront, as we can see. Now another point we should discuss, that if there is a point source, but the distance between the point source, suppose is a point source, but the distance towards the observation is really high, then this point source is converted into a planar wavefront. Now, as we can see that our sun is a spherical source of light, but obviously from Earth the sun seems to be a planar source of light, because we are really in a huge, the distance between the sun and Earth is really high with respect to our observation. That is the reason the sun seems to be a planar source of light. Now we are going to learn Huygens principle. Now what is Huygens principle? So before we start with Huygens principle, we should learn about wavelet. Now what is wavelet? Suppose this is a wave, I mean this is a wavefront basically. These are the direction of the light. Now we can consider different points in that wavefront. Now wavelets are basically whenever light is going in this different direction. So these small directions are represent the direction of the wavelet. Now Huygens principle says that every point in this wavefront can be considered as secondary source of light. Now what we mean by secondary source of light? Light is coming from some specific source, and this is the wavefront we have considered. Now we can consider any point on this wavefront. This is actually called wavefront. I mean wavelet. This is another wavelet. This is another wavelet. So there could be infinite number of wavelets, and as there could be infinite number of wavelets, these wavelets can be considered. I mean these points can be considered to be the secondary source of light, and these lights are actually called wavelet. Now, as you can see that if this is the secondary source of light, then light will propagate again in this direction by propagating these wavelets. Again, we can consider wavelets here. Again for next portion. So this is how light actually propagates. Now, obviously, this theorem, this principle, does not seems to be the really good enough in today's physics actually. But at that time, that principle was really helpful for us to explain the interference, diffraction, as well as reflection, and the refraction phenomena. Now, another thing I would like to mention in this context actually, if the law or the principles, no matter how much it seems to be imperfect, but if that principle is using that principle, if we are unable to explain that our physical observation, then no matter how weird the principle seems to be, it is considered to be true, because that principle, using that principle, we are actually unable to explain our physical explanation, physical observation actually. Now, Huygens principle does not seem to be really good enough, because there we need to consider wavelets, there we need to consider secondary source of light, and that's all. But the thing is that using that concept, we can actually explain the interference as well as diffraction, and we can bridge between the reflection and the refraction phenomena. So the motto of physics is to bundle up or to sum up different physical theory and different concepts, different formula actually. So this is the basic motto of physics. Now, using Huygens principle, we can actually bundle up these 4 different physical explanation. So that is the reason, although the theorem or the concept seems to be really weird for us, we can explain the physical. We consider the physical theorem to be really good enough. Now, we will try to prove law of refraction and law of reflection using Huygens principle. So let us start. Now let us start with the proof of reflection. Suppose this is a mirror. Now a ray of light is made to fall on this mirror. So suppose this is M1, M prime. So this is a mirror. Now a beam of light is made to fall on this mirror like this. Now, as the beam of light, it will be reflected. So we'll try to draw the reflection. Now, if this is the normal and this is also the normal. Now, we need to draw the reflected light. So this is the incident light and this is the reflected light. Again, this is the incident light and this is the reflected light. Now, we are going to extend that portion. Now we are drawing this line parallel to this ray, and again we are extrapolating this portion parallel to this actually. Now this is D, and we are drawing another ray like this. Now this is P. Now P may be any point between A and A prime. So this is A, and so first we'll try to prove the law of reflection by using Huygens principle. Now what does the law of reflection says? Law of reflection says that angle of incidence equal to angle of reflection. Now we'll try to prove this law using the Huygens principle. Now this is a mirror, and there is a beam of light which is made to fall on this plane. This is A and this is A prime. Now if this is a beam of light, then we need to consider the wavefront. So here this is a beam of light, so the wavefront should be planar wavefront. Now this is B and this is the wavefront. Now we'll try to draw the normal. Now this is the normal, and again this is the normal. Now this is the reflected light, and again this is the reflected light. Now one thing, don't get confused with these and these lights, these lines. This AB represent the wavefront, and this line is the, this one is the reflected light. So don't get confused with AB and this line. Now we will be extrapolate to defined line. First we will extrapolate that light. So here we will name it D, and that D we are actually again extrapolating this. This is D. Now we are naming the normal to be here N and this to be N prime. Now suppose this is light A, this is B, and this is C, and again we are drawing another line, and this is B. So this was A, so we are getting back A here. This is B, so here, and this is C, so this should be C. Obviously we have to give the direction. This is A, this is B, this is C, this is A, this is B, this is C. Now we are naming this point to be P. Now this P could be any arbitrary point. So here also we are extrapolating that portion, we are naming it Q. So this is how we can actually draw the diagram. Now if we take the length AD, and draw a triangle like this, so we are taking the equal length of AD and drawing or cutting over each other. So here we are taking the length AD and cutting that line here, so we get B prime. So this is B and this is B prime. Now this is M prime. Now we can get M prime by the similar way, by taking equal length of P. Now if this is M, this should be M prime. Now A, M, B. What is A M B? A M B is the incident wavefront. Now if the incident wavefront A M B equal to the reflected wavefront. Now what is the reflected wavefront here? Here the reflected wavefront is A prime, M prime, B prime. So this is the reflected wavefront. If the incident wavefront equal to the reflected wavefront, then we can actually get the proof of that theorem, that okay, now a light is incident and a wavefront is incident, and okay, and we are getting the same wavefront over here. So our target is to prove that A prime, M prime, B prime is the reflected wavefront. Now this is our target to prove. Now we will do some basic geometrical steps to prove that okay, this is the reflected wavefront. Now in order to prove this, we will compare some triangles. Now we'll go with some comparison. Now in order to compare the triangles, first we take the triangle A, B, A prime and triangle A, B, A prime. We'll take these two triangles. Now out of these two triangles, A prime is common. This A prime is the common arm, the first one. The second one is that angle A prime equal to angle A D A prime. Now why these two angles are equal? This is because that these two angles both are perpendicular, I mean 90 degree. So this angle is 90 degree, again this angle is 90 degree. Now our third step. So third step is to get the another angle. Now in the third step, you can see that we have taken AD equal to A prime B prime. Sorry, we have taken AD equal to A B prime. So we can, it is easy for us to say that A D A prime is equivalent to the A B A prime in all respect. So we can say that if these two triangles are equivalent, then angle A B A prime equal to angle A A prime D in all respect. So these two angles are equal. Now we'll compare another. Now we can solve this by some basic mathematical steps. First, we consider the velocity of light in that medium. Let us consider the velocity of light in that medium be v and time taken for that reflection be t. Then vt equal to the path traveled by the wave to be reflected from here to here. So t is the time taken for the wavefront to be reflected from here to here. So after that, before the time t, the wave is here. After the time t, the wave is here. Now we are taking a b prime equal to a prime b. Now a b prime is this path and b a prime is this path. So when the light is being reflected and going to this portion, another light, so here the light is striking first in this portion because it's a beam of light. So first the a portion of that wavefront is touching the surface. So in that time the wave is going to b prime. Now in that time the another point of that wavefront, so this is A, now this is the end point of the wavefront, this is B, is crossing that distance. So this is A prime. So these 2 points, these 2 distances are actually equal. This distance and this distance are actually equal. And according to our drawing, that AD is equal, so AB prime equal to BA prime equal to AD equal to VT. So this is the distance that the wave is traveling for the reflection phenomena. Now, here obviously we can take AB prime equal to AD. AB prime, this is AB prime. AB prime equal to AD. And obviously AB prime A prime equal to angle AD A prime. AB prime A prime equal to AD A prime. Now why AB prime A prime equal to AD A prime? Because as you can see, AB prime A prime, this is actually 90 degree, and AD A prime, AD A prime is also 90 degree. Now this A prime is the common in these 2 triangles. So we can say that this A prime B. Now what is A prime B? A prime B. So this angle equal to this angle A prime D equal to this angle. So we can say this. Now so these 2 angles are equal. So we can say A prime, B prime. So this is A prime, B prime equal to A prime, D. So A prime, B prime equal to A prime, D. So these triangles are equal. Now, if these two angles are equal, these two angles can also be called in a way that A prime, M prime equal to angle A prime, Q. So these are the same. We are just replacing B prime by M prime and D by Q. So we will need this in our next step actually. So what is our next step? Our next step is to compare two different triangles. Now what are these triangles? Now the triangles are triangle P Q A prime and triangle P M prime A prime. So we will compare this triangle. Now first one is already proved that these angles are equal. PAQ prime and PA prime M prime are equal. Now what is our second step? Our second step is to compare another angle, that these angles. So these angles are also equal because these are the 90 degree. We will write this in a form P angle PQA prime equal to angle P M prime A prime. And what is our third step? Third step is P A prime. So this is the common actually. P A prime is the common actually. So these two triangles are equal in all respect actually. So we can write that P M prime equal to P Q. So P M prime equal to P Q. Now as we can see that if the mirror was not there, then this is supposed to be the wavefront. So AB was supposed to be at A prime D if the mirror was not there. Now if the mirror is there, the wavefront is being reflected at A prime, M prime, B prime. So A M B is converted into A M prime, B prime. So this was our target actually, to say that after being reflection, that the wavefront A M B is converted into A M prime, B prime. This was our target, and our target is actually fulfilled. So we can say that by the reflection, the wavefront is being converted into another wavefront. Now we'll try to prove the law of reflection. Now what does the law of reflection says? Law of reflection says that I equal to R, angle of incidence equal to angle of reflection. Now this is our I and this is our R. This is our R. Now if this is I and this is R, then this will be also, if this is I, then obviously this is also I. We'll try to understand this. So this is the point. We are drawing a normal. This is A, N is the normal, and this is the incident light. So A prime, sorry, A capital A is the incident light, and the reflected light is A B prime. Now this is I, this is R. Now, as you can see that if this is I, we're taking another ray, we're drawing a normal here, and the normal is B. So this is the normal. So this angle should also be I, because if this angle is theta, then I plus theta equal to 90 degree here, according to this, and according to this portion also, according to this portion, I plus theta, according to this portion, I plus theta equal to 90 degree, because here AB is the wavefront, so that wavefront should be 90 degree. So I plus theta equal to 90 degree. Again, if this angle NAB, so this theta here, theta means basically NAB. So this is theta. So NAB equal to theta here. Now I plus theta equal to 90 degree. Now NAB plus angle BA, suppose we are calling it A prime. So BA A prime equal to 90 degree also. So here theta plus B A prime equal to 90 degree. So we can write that B A prime equal to I. So this is the angle of incidence. Now we can write this angle to be I. Again, we will try to understand another portion, that what is this angle? That means angle A prime B prime. Now, if in the triangle A B prime A prime, if this angle is R, then this means that again so this means that this is R and this is suppose phi. So R plus phi equal to M A B prime plus M A N plus N A B prime. Now this is equal to M A B prime. So this is the angle, and according to the property of the triangle A B prime A prime, we can write this angle to be equal to angle A B prime A prime plus angle A prime B prime. Now this angle is 90 degree, and also this angle, this phi equal to 90 degree. So 90 degree plus R equal to A prime B prime. So we cancel 90 degree on both sides, so we get this angle A prime B prime to be equal to 90 degree. So you can write this angle to be also equal to R. To be equal to R. So we can also write this angle to be equal to R. Now this angle is I, this angle is R. Now according to our proof that I equal to angle CAN and that is equal to angle BA A prime, and R equal to angle NAB prime equal to angle B prime A. Now we all know that AB equal to BA equal to VT, so we can prove that these two angles are also equal, and so we can write angle I equal to angle R. So this proves the law that angle of incidence equal to angle of reflection. Now we'll try to solve another proof, that the law of refraction. So this is how we actually prove that law of reflection. Now we'll try to prove law of refraction. Now we want to solve the we want to prove the law of reflection. Now we want to prove the law of refraction by using the principle. Here, this is the structure, this is the diagram. First, we will draw S is prime. This is the reflector, actually, this is the refractor, actually, this is the refracting surface. Now, this A, B, C is the incident light. Now, obviously, we will give the direction of the light. Now, this is the refracted light. So, this is the incident light beam, and this is the refracted light beam. Here, A prime, B prime, C prime is the refracted light beam. If we talk about the wavefront, then this A and B is the incident wavefront, and this A, M prime, B prime is the refracted wavefront. Now, suppose T time is required for that phenomena to be happened. Now, T time is required for the entire phenomena to be happening. That means in T time, the light is traveling from here to here, and in T time also light is traveling from here to here. Now, if T time is required, then A prime B equal to V1T, because we have considered this is medium 1 and this is medium 2. Now, in medium 1, the velocity of light is V1, and in medium 2, the velocity of light is V2. So, so A prime B equal to V1T and AB prime equal to V2T. Now, we will draw the diagram. That means we have extrapolated that portion AD and PQ. Now, AD or PQ is extrapolated in such a way that this AD is parallel to BA prime, and also for the same thing for PQ, and we have joined the D and A prime. Now, as according to our image, that as these are parallel, so that A prime B should be equal to AD. So, A prime B equal to AD, and this is also equal to V1T. That means if the medium, that means if the refractor is absent, then the light will travel this portion, that means AD. Now we'll try to solve. So if this is true, then from this we will get this relation, that V2 by V1 equal to AB prime by AD. So V2 by V1 equal to AB prime by AD from this relation. Now triangle, from triangle P, A prime, M prime and A, B prime, A prime, we can see that. So from the triangle P, A prime, M prime, P, A prime, M prime and A prime, B prime. So A prime, B prime. So this triangle and this triangle. In these two triangles, we can see that this angle, that means angle A prime, B prime is equivalent to angle A prime, M prime. So A prime, B prime is equal to angle A prime, B prime. Basically, these two angles are actually equal angle, that means same angle actually. The naming is different actually. So these two angles are equal. Again, angle A, B prime, A prime, that means this angle equal to this angle A, B prime, A prime equal to P, M, A prime. So because these two angles are equal, because these are actually 90 degree. And again, so two angles are equal, that means the third angle should be also equal. That means these two angles are equivalent angle. So these two triangles are equivalent triangles. So as we know that if the ratio of the triangles, if the ratio of the angles in the triangles is equal, then the triangles are called equivalent triangle. So these two triangles are called equivalent triangle. Now if the triangles are equivalent triangle, that means their ratio of the arms should be equal. So the ratio of the arms should also be equal, because the ratio of the angles are actually equal. So the ratio of the arms should also be equal. So we can write that P M, so P A prime by A prime. So P A prime by A prime, that means this arm by this arm equal to P M prime by A B prime. So equal to P M prime by A B prime. So this arm by this arm equal to this arm by this arm. Okay. So these two ratios are equal. The ratio of the arms are equal. Again, from the triangle A prime Q. So this is A prime Q. So sorry, this shouldn't be A prime Q. This should be P A prime Q. So from the triangle P A prime Q, that means this triangle and A prime D. So that means this triangle. So from these two triangles also we can see that P A prime Q and A D A prime, here also the angles are equal and these angles are actually 90 degree. So here also from the triangle also we can actually say that P A prime by A prime, that means P A prime by A prime equal to PQ. This PQ by AD. So here P A prime by A prime, P A prime by A prime equal to PQ by AD. So we can write P M prime by PQ equal to AB prime by AD. So this is all we wanted, because our target was to show that if this is the incident wavefront, then this P, if A and B, that means in the similar way that A and B is the incident wavefront, this wavefront is supposed to be converted into A prime, M prime, B prime. So our target is full speed. So our target was to conversion of the wavefront. So we can see that these two wavefront are actually converted. So this is the incident wavefront and this is the refracted wavefront. This is the incident wavefront and this is the refracted wavefront. So our target is fulfilled. So now we'll try to deduce the law actually, that means the law of refraction. Now we'll try to prove the law of refraction. Now what does the law of refraction say? The law of refraction says that the ratio of the sine of the incident angle and the refracted angles are equal. So we'll try to prove the law of refraction. Now to prove this, first we will find out what is the angle of incidence and what is the angle of refraction. So here angle of incidence equal to CAN, because as we know that this is the incident beam and this is the refracted beam. So CAN here is the incident angle. And what is the refracted angle? The refracted angle is here N prime, A prime, A prime. So this angle N prime, A prime and small a prime. So this is the refracted angle. Now we do know that CAN equal to obviously BA A prime. Why? Because in the previous proof we have already shown that if CAN is I and CAB is 90 degree, then BA prime is 90 degree minus BAN. So these two angles are actually I, the angle of incidence. So this is, if this is I, then this is also I. So we can write I equal to CAN equal to BA A prime. Now for R, N prime, A prime, small a prime. So N prime, A prime, small a prime equal to A prime B. Now what is A prime B? A prime B. That means this small angle, this angle is R. Okay, A prime B, this angle is R. So we can write sin I by sin R equal to sin A prime equal to sin A prime. So we can write A prime B prime, A prime B prime, sin I equal to B A prime equal to B A prime, that means this angle, by sin A prime B prime, that means this angle. So this angle by this angle. So this angle is I and this angle is R basically. Sorry, R. So this is A prime, this is B and this is B prime. So sin I by sin R. So we need to figure out the relation. Now as we have already seen that sin I equal to sin B A prime equal to B A prime by A prime, and sin A prime B prime equal to A B prime by A prime. So we can write B A prime equal to A. So we can write this should be equal to A prime, cancels out each other. So this equal to B A prime by A B prime. So this is equal to B A prime by A B prime. So as you have already seen, this is equal to V1 by V2. So this is equal to constant. So this was the mu, that means the refractive index. So refractive index equal to V1 by V2. Now for the discussion I can say that we have got two different definition of the refractive index of light in our class 10 or 9 standard. Basically, if you're in the ICC standard, I hope you've learned that what is the definition of refractive index. So in your textbook there are two different definitions of refractive index. The first definition is the sin I by sin r, and another definition is the ratio of the velocity of light in that medium. So that seems to us that there are two different. Why there are two different definitions? Because different definition of same quantity is not possible. So in physics, another thing is that different definition of same physical quantity is not possible. So that means I am more or less giving the same thing actually. So as you can see that mu equal to sin I by sin r, that is equal to v1 by v2. That is the reason the refractive index can be defined in two different ways. The first one is sin I by sin r, and the second one is v1 by v2. So obviously v1 by v2 equal to constant. So our target was to show that sin I by sin r equal to constant, and if sin I by sin r equal to v1 by v2, then our target is fulfilled actually. So that's all. Now I hope you have learned how we can prove that what is Huygens principle, and how we can prove the law of refraction and law of reflection from the Huygens principle. That's all. Now I will go ahead and discuss about something more about this chapter. So thank you.